All right, we are in section 4.4 now, and we are returning to the topic of limits in this section. We discussed limits at length in chapter 2, and we talked about lots and lots of different ways of solving them using different laws that we came up with, different techniques and rules and things like that. But with that said, there's a lot of limits that would resist the techniques that we came up with in chapter 2. Here, this one is one such example. The limit as x approaches 0 of e to the 2x minus 1 over sine of x. If you look at the numerator and denominator of this quotient, this rational expression here, if you were to try direct substitution, you would find that you get 0 over 0. And we saw that kind of thing happen a lot back in chapter 2. Our usual technique there was to try and do some sort of algebraic manipulation of this to get some things to cancel out. Like if these were both polynomials, we would try and factor those polynomials, and usually something would cancel out. And then the remaining stuff would work with direct substitution. But nothing like that happens with this function here. What we want to do is be able to evaluate limits of this type and several other types that we're going to see soon. So the reason this is appearing in chapter 4 is all about applications of the derivative. It's showing up here because it turns out that these limits can be evaluated using derivatives. And that's what we're going to get to very soon. So before we can talk about that, how the derivative is used in that way, we need to introduce a new term. So the term is called indeterminate form. Limits of this type are what we call up here, are what we call indeterminate forms. And rather than give a general definition for what an indeterminate form is, we're going to talk about the several different types or the several different forms in which these things occur. But basically what an indeterminate form is, without getting too technical, is it's a limit that resists the techniques of chapter 2. That's how we're going to think of it. An indeterminate form is a specific type of limit where direct substitution is not going to work, and simplifying oftentimes doesn't help. So right now we're going to introduce two types, and that's going to lead us into the technique that we use to solve them. So we have an indeterminate form of type 0 over 0, which we'll talk about right here, and then another indeterminate form of type infinity over infinity. So what this means when I say an indeterminate form of type 0 over 0, first of all, we're talking about a limit. So expressions by themselves are not indeterminate forms. It has to be a limit. But it's a limit of the form f of x over g of x as x goes to a, where the limit of each of the functions in the numerator and denominator both go to 0 as x approaches a. That's what's being said here. So usually we check that using direct substitution, because in I think all of the examples that we do here, we can evaluate the limit of this f of x and the limit of this g of x as x approaches a by direct substitution. But we end up with 0 over 0 if we do that, which we know it gives us no information. The limit will very likely exist, but direct substitution is not giving us that answer that we're looking for. Another type of indeterminate form is very similar to this one, where you're looking at a limit as x approaches a of f of x over g of x. And both of these functions go to either positive infinity or negative infinity. And you can have one of each happening as well. You can have f of x approaching infinity while g of x approaches negative infinity, both as x approaches a. In those cases, infinity is not a number, and so it's tempting to just say, well, the limit doesn't exist. But it might, right? Because if these are both growing towards infinity, for example, they might be balancing each other out with this division that's happening here. So that limit may still exist even if the individual limits of this numerator and this denominator both go to either infinity, positive or negative infinity, or both. What I want to do is discuss this thing called L'Hopital's rule. And L'Hopital's rule is the main subject of this section. It's the rule that tells us how we can evaluate these limits. Okay? So the way L'Hopital's rule works is we have one of these two indeterminate forms, the 0 over 0 type or the infinity over infinity type. If the functions f of x and g of x are both differentiable, and if g prime of x is not equal to 0 on an open interval I containing the number a, which is what x is approaching. If we suppose that the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0, so this is setting us up for this first indeterminate form, or if those limits approach positive or negative infinity each, which, like we said, is just saying that it's of one of those, the limit as x approaches a of f of x over g of x is one of these two types, then L'Hopital's rule says that this limit is equal to the limit as x approaches a of f prime of x over g prime of x, okay? And what this means is that if we encounter one of these indeterminate forms, f of x over g of x, where the limit as x is x approaching some number a, which can also be infinity or negative infinity. A can be positive or negative infinity or a finite number. If this limit is an indeterminate form of one of these two types, then we can try and evaluate it by taking the derivative of the numerator and denominator and then applying the limit to that new expression. That's what L'Hopital's rule says, okay? Now you should look at that and think that's weird that that works, because the derivative doesn't seem to have anything to do with this kind of a limit. It just seems like a magic trick. And we're going to do several examples involving this, but L'Hopital's rule can be proven using something called the generalized mean value theorem. I think it's also called Cauchy's mean value theorem. We're not going to go through that proof here. I think it shows up in Appendix F of your book. But there is kind of an intuitive argument that you can make. So if you have these two functions, if we look specifically at the case where we have an indeterminate form of type 0 over 0, then the graphs of f of x and g of x might look something like this. So you notice here f of x here, g of x here. Excuse me. They both are approaching 0 as x approaches a. In fact, it looks like both of them have an x-intercept exactly at a. But that would be the case for these two functions. So that makes f of x over g of x, or the limit as x approaches a of f of x over g of x, the 0 over 0 type of indeterminate form. Now, if we were to look at the tangent lines at a for both of these functions, they might look something like this. So here's the red line. This is the tangent line corresponding to f at a, and the tangent line at x equals a for the function g of x right here. The slopes of these functions, let's call them m1 and m2, okay? And I know this is really small over here. I copied and pasted this out of your book. But basically what this is saying is that if these two functions were actually linear functions, then f of x over g of x would look like this. m1 x minus a over m2 x minus a, because that's the equation of each of these tangent lines, okay? But the x minus a's would then cancel each other out, giving me m1 over m2. And we know that if we're taking the limit as x approaches a, x is never actually equal to a. So the fact that there's a 0 down here in our denominator, if you plug an a in directly, is irrelevant, because we're dealing with a limit. So if f of x and g of x were actually these lines instead of these curves, I can see that the ratio of f of x over g of x is just the ratio of their slopes. But of course, m1 would be f prime of x in that case, and m2 would be g prime of x in that case, because those slopes are what the derivative gives us. Now, these curves are not tangent line. They're not straight lines, they're curves. But we know that when we're close enough to a, the tangent line serves as a good approximation. These are the linearizations of these functions at x equals a. So as decent approximations, we would expect this to be approximately the case in the case of f of x over g of x when x is near a. And so in the limiting case, that approximation becomes exact. The limit as x approaches a, the f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, those slopes. Now, it's not a proof, that's just an intuitive argument. So again, the proof is much more involved, and you're welcome to go check it out if you want. We're just not going to use our time for that. So let's get into some examples. Okay, here's the example I had shown at the beginning of the section here in the lecture notes. The limit as x approaches 0 of e to the 2x minus 1 over sine of x. Now, in order to use L'Hopital's rule, you have to first verify that you're looking at an indeterminate form. It doesn't just apply to any limit that looks like a quotient. It has to be an indeterminate form or it doesn't actually work. But this is an indeterminate form of type 0 over 0, because if I try to directly substitute 0 into both of these expressions, in my numerator I get a 0, in my denominator I get a 0. That means I'm looking at one of those indeterminate forms. So L'Hopital's rule is going to apply here. Okay, I feel like my camera's getting all blurry all of a sudden. So what's going to happen is I'm going to write this limit, the limit as x approaches 0 of e to the 2x minus 1 over sine of x. I'm going to use L'Hopital's rule, which says that I simply take the derivative of the numerator and denominator separately. The derivative of my numerator is 2e to the 2x, and the derivative of my denominator would be cosine of x. L'Hopital's rule says that this limit is equal to this one. And this one I can evaluate by direct substitution, because if I plug a 0 into my numerator now, I get 2 times 1, or 2. If I plug a 0 into my denominator, cosine of 0 is 1. So the answer is just 2. Notice that would not have worked if I tried direct substitution here. Again, 0 over 0. That's not equal to anything. But L'Hopital's rule gets me there. Okay, so that's the power of this rule. Let's look at some other examples. Here we have the limit as x approaches infinity of the natural log of x squared. Excuse me. So if I tried taking the limit of this numerator and this denominator separately, I would see that both of these go to positive infinity, which means we're looking at an indeterminate form of type, I don't know why I wrote an 8 there, infinity over infinity, okay? L'Hopital's rule would apply here as well. So if I wanted to find the limit as x approaches infinity of the natural log of x squared over x, this will be equal to the limit as x approaches infinity of the derivative of this function over the derivative of that function. Now, what is the derivative of the natural log of x squared? That would require the chain rule. So that I would take the derivative of the outside function, 2, leave the inside function alone, and then multiply by the derivative of the inside function. Okay? Now this is equal to, the derivative of x is just 1. Okay? And this guy, limit as x approaches infinity, I can simplify this a little bit. So the 1 I can get rid of. It becomes 2 times natural log of x times 1 over x, or 2 natural log of x over x. Same thing, okay? So I've used L'Hopital's rule to get from here to here, and then getting from here to here, I'm just simplifying this. I haven't used L'Hopital's rule again. But I'm going to have to do that, because if you look at what we're dealing with here, we have yet another indeterminate form. So this limit, this limit up here goes to infinity, and this one goes to infinity as well. We have another infinity over infinity type. Because this limit is still an indeterminate form, I can apply L'Hopital's rule a second time and take those derivatives again. So this becomes the limit as x approaches infinity. The derivative of my numerator is 2 over x, and the derivative of my denominator is 1. Okay, this is the same thing as the limit as x goes to infinity of 2 over x. But as x goes to infinity, notice my numerator is constant. This is no longer an indeterminate form, but I can evaluate this directly. This is equal to 0. Okay, we've dealt with lots of limits of this type. The denominator grows very, very big, while the numerator stays at 2, and so this is shrinking down. It's getting smaller, approaching 0. All right, let's take a look at another example. I'd like to evaluate the limit as x goes to 0 of x squared sine of x over sine of x minus x. This is a more complicated looking one. Is this an indeterminate form? Try direct substitution and see what happens. If If I plug a 0 into my numerator, 0 squared is 0 times sine of 0, of course, is going to be 0. Plug 0 into my denominator. Sine of 0 minus 0 is equal to 0 minus 0, which is 0. So this is a 0 over 0 indeterminate form. I can apply L'Hopital's rule to this guy as well. So the limit as x approaches 0 of x squared sine of x over sine of x minus x. Take the derivative of your numerator and denominator separately. And I want to point something out. I think when I've taught this class in the past and I've done L'Hopital's rule, people get confused because they look at that f prime over g prime and they think, they try to mix it up with the quotient rule. Obviously, it's not the quotient rule. We're not doing anything with the quotient rule here. It's a completely different thing. L'Hopital's rule is just what we've been doing these last couple of examples. I take the let me write my limit. Limit as x approaches 0. The numerator is a product, so I need to use my product rule. X squared has a derivative of 2x. That becomes 2x sine of x plus x squared times the derivative of sine, which is cosine of x. Now if I take the derivative of my denominator, sine is going to have a derivative of cosine of x. X is going to have a derivative of 1. So that's what I end up with after using L'Hopital's rule. Now, if you take a look at this, you'll notice that we still have a problem because the derivative of if I use direct substitution, I have a 2x here and an x squared here. So plugging 0 into each of these is going to give me 0 plus 0. Cosine of 0 is equal to 1, and so I have 1 minus 1, which is still 0. I still have an indeterminate form here. So that means, like the previous example, I need to use L'Hopital's rule a second time so that I can hopefully get this thing down to an expression I can take a limit of directly. So looking at this now, the derivative of this numerator up here, I have two product rules that I'm going to use here. So this becomes 2 sine of x plus 2x cosine of x. That's the product rule applied to that first term. Plus 2x cosine of x. I'm using the product rule here now. Plus x squared times negative sine of x. So maybe I should, I'll make this negative sine of x, then I'll simplify. My denominator, the 1's going to go away. Cosine becomes negative sine of x. Okay, let's simplify a little bit. This becomes the limit as x approaches 0. I can combine these two, and I end up with 2 sine of x plus 4x cosine of x minus x squared sine of x, all over negative sine of x. All right. So looking at what we have here, it still appears that we have some problems because, again, if I plug 0 in directly, the 4x here and the x squared here are both going to become 0. So I have 0 here and here. Sine of 0 is also equal to 0. So I have 0 plus 0 minus 0. The whole thing equals 0. Sine of x, plugging a 0 into that, is still 0. I have my third 0 over 0 indeterminate form. Now, don't worry. I mean, this is fairly common with these problems. You may have to use L'Hopital's rule multiple times. It's not necessarily implying that this is just going to happen over and over and over again and never stop. So let's try it one more time and see what happens. Limit as x approaches 0. I'm taking the derivative of my numerator. 2 sine of x becomes 2 cosine of x. I need the product rule here, so this becomes plus 4 cosine of x minus 4x sine of x. That's the product rule applied to just this right here. And then minus, let's put this in parentheses so we're careful with our minus sign, 2x sine of x plus x squared cosine of x. Okay? All over negative cosine of x. So I'm expecting this now to not be an indeterminate form anymore because my denominator is going to come out to -1 if I plug 0 in directly. So what I'm going to try and do is simplify some things here. This becomes the limit as x approaches 0 of, I have a 2 cosine of x plus 4 cosine of x. So that's 6 cosine of x minus 4x sine of x, and then I have a minus 2x sine of x here when I distribute that minus in, so I can write that as minus 6x sine of x, and then this becomes minus x squared cosine of x, all over negative cosine of x. Now, if you notice, I can actually use direct substitution this time. If I plug 0 in directly, I get 6 times 1, which is 6, minus, if I plug a 0 into this x, that whole term goes to 0. And if I plug a 0 in for that x squared there, I get another minus 0. Down here, I get -1. This whole thing becomes -6. Okay? So that took 3 applications of L'Hopital's rule, but we eventually got there. All right. So, go all the way to the top here. Now that we've covered a few of these, we're going to look at some other indeterminate forms. So when we introduce indeterminate forms at the beginning of this section, we said that they come in those types 0 over 0 and infinity over infinity. But we didn't say that those were the only types. They do come in other types as well. So there's 5 in total left to talk about, which we're going to go over right now. And actually, I'm looking at these. I think I'm going to save this last part for the next part of this section.